Hey guys, so this is our group's T520 module on girder stability and introduction to materials and hanging girders. This is group E, and we are Sarah White, Tinsley Martin, and T Hobbs. So, just a little overview. We are going to be talking about lateral stability, rolling axis, girder stability, factor of safety, and hanging girders. So, first off, lateral stability. So, lateral stability advances in the industry have allowed cross sections to be optimized to take advantage of larger strand diameters and greater concrete compressive strength, which allows for much longer spans. These improvements are greater for the industry, but lateral stability still must be considered. And just like a little what's on the page, it's optimizing girder shapes and allows longer span lengths. Like I said, they're mostly going to be over like around 180 feet, but most likely will also increase in length as well. Um, these so it says these girder shapes have improved stability characteristics such as wide top flanges and wide bottom flanges. So now, this is the limitations of the recommended practice, and it's um the information that we cover are applicable for I sections, bulb tees, or deck bulb tee sections, or wide flange sections, not box girders or U sections. So, the information, yeah. So, yeah. And that's like what's at the bottom is like examples of what each one is. That, like, to the right, you see the box girder and the U section girders, and to the left is the bulb T, the I beam, and the T double deck bulb T. Next, we're going to talk about the roll axis. So the roll axis is a line that connects the two support joints of a girder about which a girder can rotate. The key to defining the roll axis is defining the points where the girder can rotate about. If girder is hanging, the roll axis connects the 2 points where the girder is connected to the lifting cables. If lifting loops are used, the roll axis is taken as the top of the girder. For rigid lifting devices, it is taken as the point where the device is connected to the lifting cables. For a seated girder, the roll axis connects the top surface of the bearing pad or support on which the girder sits. All girders have slight imperfections, so the center line of mass, so the center of mass of the girder may be displaced significantly with respect to the roll axis. This causes the girder to tilt to bring the center of mass under the roll axis. If the supports rotate, this may lead to beam instability. And now we're going to move along.
Okay, now I'll talk about girder stability. Um, so there are five main phases over the life of a precast pre-stressed concrete girder, and those five phases are lifting, storage in the pre-stressing yard, transportation to the site, erection, and construction. Over all the phases, the lateral stability of the girder must be considered and checked. At any time where the girder is lifted, there may be no rotational restraint at the lifting hooks, meaning lateral instability is always possible. When stored, the girder is placed on a wooden dunnage with no rotational support. During transportation, the girder's stability may be affected by the truck stiffness, wind load, centrifugal force, or change in the wheel path. When erected, the girder must be properly braced to prevent rotation on the supports. Construction loads may also cause lateral instability of the girder. This is why during each stages of the girder, you have to consider lateral stability. So next we'll cover the criteria for girder stability. Um, the analysis of girder stability should conform to the accepted industry practice. Um, the recommended practice establishes criteria pertinent to the design of precast pre-stressed concrete girders, lifting devices, bearings, and bracings that may be required to provide an acceptable factor of safety for lateral stability. The four main criteria for girder stability must include defining the assumed design and construction loads, identifying assumed material properties, specifying tolerances for construction, and establishing stress limitations and overall factors of safety. Um, Continuing on to the girder stability design and construction loads. Um, Assumed design and construction loads typically consist of permanent loads, transient loads, and environmental loads. Some of the permanent loads that are considered are the dead load of the structural components and the pre-stressing force due to creep and shrinkage. Some of the transient loads that are considered are the dynamic loads, centrifugal force, and construction live load. The environmental loads that are considered are the wind loads, thermal effects, and seismic loads. So going a little bit more in depth on the dead loads of structural components, one of the big considerations is concrete unit weight. The normal weight of reinforced concrete is assumed to be 150 PSF, or sorry, PCF. Lightweight reinforced concrete unit weight varies from 100 to 140 PCF. Heavily reinforced dense concrete may be as high as 170 PCF. The weight of falsework and supports must also be considered. The ASHA Guide Design Specifications for Bridge Temporary Works from 2008 specifies a minimum of 160 PCF for normal weight concrete and 130 PCF for lightweight concrete. This includes the weight of the reinforcement and the falsework of the beam. Actual dead loads depend on the materials used in fabrication of the girder and construction of the bridge. The engineer should always have a knowledge of the materials used and adjust the calculations accordingly. The next category we'll discuss is the factor of safety. The factor of safety against cracking is defined as the resisting moment divided by the active moment that you can see in the equation down at the bottom. Um, this is also the factor of safety based on the equilibrium post cracking. Um, Mast, who wrote one of the governing books about factor of safety and girder stability, recommends that the factor of safety should be greater than 1, that we can also see down here at the bottom. Next, we'll talk about the cracked section angle of rotation, also having to do with the factor of safety against failure. Um, so first of all, theta is varied to find the maximum factor of safety. Um, And by differentiating the equation for the factor of safety against failure with respect to theta, the maximum tilt angle can be computed. And the maximum tilt angle is what will be used to find the factor of safety against failure. Um, that maximum tilt angle should be less than or equal to 0.4 radians. And the factor of safety against failure should be greater than or equal to 1.5. Um, and for crack section angles of rotation, the sections along the length of the girder should also be checked to ensure that the girder has adequate lateral moment capacity to resist 1.5 times the active moment. It's important to note that the factor of safety, if the factor of safety against failure, Fs prime, is less than the factor of safety against cracking, which is just Fs, the maximum factor of safety occurs right before cracking. Therefore, Fs is equal to Fs prime.
Next, we will cover hanging girders. For wind loads, the following two equilibrium conditions must be considered. The left is where the wind load increases rotation and decreases lateral deflection, and the right is where the wind load decreases rotation and increases lateral deflection. From this, we can gather that the rotation and deflection have inverse relationships with similar wind loads. In both diagrams, E sub wind is taken as the eccentricity of the girder weight for the girder subjected to the wind load, Ws. Eccentricity is negative when the wind load increases rotation and decreases lateral deflection, and positive when the wind load decreases rotation and increases lateral deflection. These two cases will be further discussed in the next few slides. We are given an equation at the top, and that is for our active moment. Here Z sub wind is the lateral deflection due to Ws. It is computed using the span um, between the assumed support or lifting locations. And then by using the small angle approximation that cosine theta equals 1, we have a new active moment equation. The next two slides will outline the derivation of the equilibrium equations due to wind increasing and increasing rotation and decreasing lateral deflection. So here we're given the new MA or active moment equation, and then MR is the resisting moment equation. The equilibrium angle can be found by setting MA to MR and then solving for the angle. Fs and Fs prime can be found by dividing the resisting moment by the active moment. Wind force can be strong enough to cause a girder to tilt in the wrong direction. To account for the equilibrium angle going in the wrong direction, the value will become negative, thus modifying the equations to account for the reverse tilt.